Well, hello and welcome back. Welcome to Lecture 2-2B on Probabilistic Robotics, and we're going to look at modeling actions today. We're going to examine how a robot acting in a dynamic world affects the state estimation process, and then review the Bayes filters framework when we add in this modeling of actions. So, often a world is dynamic, especially when you're talking about mobile robotics, because we know that actions can be carried out by the robot, actions can be carried out by other agents, time is passing. We know the world is not going to be static. There's going to be changes based upon other agents as well as the robot. So the question becomes, how do we incorporate these actions into our state estimation or our belief or confidence in the robot's actions or in sensor data that we receive? So these actions increase uncertainty in state estimation. So for example, I have a robot and the robot senses an apple and a banana or some fruit, and then the robot now moves. So the robot has to have a sensor certainty that is the fruit still where I left it? Did somebody pick it up? Did someone eat it? The robot also has to have action or motion confidence in that it just moved. If there's sensors, encoders, etc., did it actually move to where it thought it did? Is it still even in proximity to the fruit, etc.? So typical actions could be on a mobile robot, its wheels turn, did it move, how far did it move, etc. If you're talking about a robot manipulator or a mobile robot with a gripper, then it could be grasping an object such as grabbing a knob to open or close a door. So we can never carry out these actions with complete certainty. So as we talked about before, a lot of times with a belief, we're trying to exceed a certain threshold in order to make decisions about how to move. In contrast to measurements, which we talked about in the previous lecture, these actions generally will increase uncertainty, although with measurements, we hope that they would increase certainty of some certain condition in the environment. So thinking about what we discussed before with the robot going through the door and having to model the actions, what is the probability that the door is open if the robot moves and it was closed before? So to incorporate the outcome of an action, we now use U to represent the action into the current belief that we have, and we use the conditional probability density function, or the PDF. So the probability of the current state X, given that the robot made an action U, moved, and that we knew the previous condition of the door, X prime. So this term specifies that executing U changes the state from X prime to X for the door, being either open or closed. So for the closing the door example, assume the robot executes a closing action on a door. What is the probability that the door state is actually closed? We don't know. We can't say with confidence because the gripper may have slipped, the robot may not have actually reached the door, etc. So we would have the following state transition diagram for the robot closing the door. The probability that the door is closed, given that the robot has made a closing action and we knew the previous state of the door. So if the door is open and the robot makes this action, then the probability is 0.1 that the door is still open. It's 0.9 that the door is closed. Or if the door was currently closed and the robot makes a closing action, we are 100% confident the door will still be closed. And we don't have any action for if the state is closed and the robot opens the door because the robot is only doing a closing motion. So we're going to integrate the outcomes of these actions into our probabilities. So for our continuous case, the probability of X given Y is the integral of the probability of X given U and X prime and the probability of X prime dx prime. In the discrete case, the probability of X given that action would be the summation, the probability of X given that action and the previous state X prime, times the probability of X prime given the action U. If we once again make an independence assumption stating that we can get rid of U in the second sum because there is no reliance on the state of the previous state on the robot's action, then we can rewrite this as the probability of X given U is the summation over all X of the probability of X given U X prime times the probability of X prime. So now we have the resulting belief for closing the door example. So the probability that the door is closed, given that the robot has executed a closing action, would be the summation of the probability that the door is closed given the action in the previous state of the door times the probability of the previous state of the door. So we're going to have two. One of them assuming the door was previously open, one of them assuming the door was previously closed. So the probability the door is closed given the action and the door was previously open times the probability of open is 9/10 times 5/8. And the probability that the door is closed given the action and that the door was previously closed times the probability of the door being closed is 1 times 3/8. So that gives us 15/16. So now the question becomes, what about the probability that the door is open given that the robot performs a closing action? So you could go through this analysis very similarly, and what you'll see is that the result is 1/16. So you could go through all that math and get 1/16, or just know it's 1 minus the probability that the door is closed given the robot's action, because 15/16 plus 1/16 has to add up to the total probability, which is a 1. And this concludes modeling actions using Bayes' rule. I hope you've enjoyed it. I know it's a lot of math, but I hope you're getting it and you're getting something out of it. You may have to watch some of these videos more than once because this stuff gets complicated. Have a robotastic day.